Hi, Wild listeners. I just wanted to hop on and say thank you to those of you who've been giving us great feedback about our new behind-the-scenes content over on Patreon. I've recorded some fun, relaxed chats with my buddy Ken about what it's like to make the wild. We're calling it The Wild Side. If you want to check it out, you can find the link to our Patreon in the show notes of this episode. Okay, enjoy the show. I don't know about you, but I'm always pondering the big picture of things, the planet and life, what it's all about, where it all began. And a few months ago, I came across a man obsessed with equally big thoughts.
To think that there is this pulsing, breathing system out there in the void, in this big cosmos of mostly emptiness, nothingness, extremely harsh conditions. Most planets are not alive. They never come to life.
This pulsing, breathing system in the void, this system that we all call Earth, really is alive in ways that are hard for us to imagine.
Here we have this incredible miracle of a planet that not only came to life, but has remained alive, has kept itself alive for more than 4 billion years, and we get to be a part of that.
When I encountered this big thinker, author and science writer Ferris Jabr on the web, he was talking about how Earth gave birth to life, but also how life and the organisms on Earth then began to shape the planet physically, down to the rocks and the weather and the oceans. Take the Amazon rainforest, for example. Ferris had an experience that really shaped his understanding of our living Earth in the rainforest of Brazil. Half the rain that falls in the Amazon each year is created by the forest itself, an act of self-regulation, just like a living organism. To see this process in action, Ferris decided to climb up a ladder, a really long ladder, to the top of a 1,000-foot research tower, the tallest structure in South America.
It's very intimidating when you're on the ground looking up. It's this massive structure. It sort of reminds me of one of those ladders you might climb to reach a utility line or a power line, except it much, much, much larger, much taller.
There's no elevator, no safety barriers, just 1,500 slippery metal steps up.
You're harnessed to the railing just in case you slip through one of the many gaps.
It took him over an hour to get to the top of the tower, but it was worth the climb. From this perch, he really saw and understood that the millions of trees and plants in this continent-sized ecosystem pull huge volumes of water from the ground, and whatever they don't use, they release into the atmosphere, where it combines with tiny biological particles in the air and creates rain.
And then because the Amazon is so massive, spanning essentially a continent, it influences weather around the world as well. So what happens in the Amazon contributes to precipitation as far away as the Pacific Northwest in Canada. Learning about this, it sent me on a journey of looking for similar examples of how life changes the planet.
It's all in Ferris's latest book, Becoming Earth, How Our Planet Came to Life. It took him around the world, searching for more examples like the Amazon effect. And now he believes that life doesn't just exist on this planet, but the planet itself is alive. An idea that locked in his brain while he was up that tower.
When you're up there, you don't see individual trees or organisms so much. What you see is one big ecological fabric that just keeps stretching away from you.
So prepare yourself for a sweeping conversation as Ferris Jabr transports us from the cosmos to the microscopic microbes in the soil of your backyard. How forests and big wild animals like elephants and whales shape the world we live in too. All part of this pulsing system that has been operating in some pretty wild ways for billions of years. As Ferris says, life is Earth animated. From KUOW in Seattle and Chris Morgan Wildlife, welcome to the wild. Where are you right now?
I'm in Portland, Oregon, in the Pacific Northwest.
I love the backdrop there. There's a lot going on that wall that speaks volumes about who you are and what you love. Framed insects and things there, I see, and plants.
Yeah, a little natural history illustration collection in the background in my office here.
I love it. Mine's got sort of bear tracks on the wall and animal furs and things like that. We're cut from the same cloth, I can already tell. You've said that Earth is a planet that came to life, not that there is simply life on it. When you say that the planet came to life, what do you mean specifically by that?
Yeah, so let's go back in time, let's say 4 billion years ago, only about a billion years after the planet's formation. And we have this Earth that was so drastically different from the Earth we know today. It probably had this hazy orange atmosphere. It had a vast ocean that might have been dotted with volcanic islands, but didn't really have any substantial land masses or continents as we know them. And life did not yet exist. And so where did life come from? Well, the only place it could have come from was the raw materials of the planet itself. So you have all this rock and water and air. And ultimately, it was those raw materials rearranging themselves that is the process of the origin of life. So Earth's own inanimate materials rearrange themselves into the first living, self-replicating entities.
How does life come from nothing? How does life come from a rock? It feels like alchemy in some ways, but what do you mean by that?
Yeah, it is a form of alchemy in the sense of a profound chemical transformation. Earth's raw materials can be broken up into rock, water, and air. Basically everything Earth is made of is one of those things. And life is also made of those raw materials. And so as far as we know, the first self-replicating entities, the first life forms on our planet, were necessarily made out of the planet's own rock, water, and air. And exactly how that happened is still being worked out. We don't know for sure. But what we think is that it was wherever there was the right combination of chemistry and energy. So you kind of need a freely available source of energy, whether that's geothermal heat coming from within the planet or sunlight bathing the planet, some form of energy. And then you need the right chemical concoction, the right mix of chemicals and compounds. And when you have those two things together, sometimes you will get certain molecules and compounds forming spontaneously. So they're attracted to each other. They start to form longer, more complex chemicals and chemical compounds. And then some of those molecules will start making copies of themselves. And that's what we think was essentially the origin of life. It's when you have that right combination of chemistry and energy on the really ancient Earth. And we had complex molecules forming, and they started to make copies of each other. And all of that is coming from the Earth's own raw materials. So it really is bits and pieces of ancient Earth making copies of themselves for the first time, and then eventually forming the first self-replicating cells.
Let's sort of go to this sort of big picture, because all of this reminds me of an environmental theory that was very popular when I was in grad school in the 90s. Talk about ancient history. And I loved hearing about it back then. And it's called the Gaia hypothesis. And I know that you've looked into it pretty deeply. What is it, and where did this idea come from?
Yeah, so the Gaia hypothesis was conceived by a British inventor and scientist named James Lovelock in the late 1960s, early 1970s, and then he later developed it with American biologist Lynn Margulis, amongst others. And it says that wherever life emerges, it will inevitably transform its home planet, and that together life and the planet form a single, connected, self-regulating living system. And it was highly controversial when he first proposed it. His first book on Gaia was published in 1979. It was immensely popular with the general public and with this growing environmental movement, but a lot of scientists harshly criticized it because they didn't like the idea of saying that Earth itself, that the planet was alive. And they really didn't like the idea of saying that Earth was this giant organism because, organism has a very sort of strict definition in biology. Organisms are individual members of species. They're defined by reproduction and evolution by natural selection. And Earth doesn't really fit that paradigm. It's not reproducing with other planets. It's not passing down a genome, from one generation to the other. But over time, Lovelock and Margulis refined their ideas, and they really became an important part of the foundations of this relatively new science called Earth System Science, which deliberately studies the animate and the inanimate components of our planet as a single integrated system. It takes this explicit holistic view. And, it's now widely accepted that, yes, life is a profound geophysical force on the planet. It has dramatically altered the planet over billions of years. And that together Earth and life are a single interconnected system. And many scientists agree that this system does have a capacity for self-regulation, which is one of the key properties of all living systems, is that they are able to maintain and regulate themselves. I think we always have to come back to this astonishing fact that Earth, as a system, has endured for more than 4 billion years, despite suffering these incredible catastrophes many times over that have eliminated most of the life, most of the species that existed at the time. And yet every single time, Earth has not only recovered from that, it hasn't just hobbled along, it has actually flourished, after every one of those catastrophes. And it's arguably the most complex, the most biodiverse, the most alive today that it has ever been, throughout its entire history.
That's an amazing thought. It's a precious thing for us to look at in that way.
Absolutely. It's this astonishing resilience, to think that there is this pulsing, breathing system out there in the void, in this big cosmos of mostly emptiness, nothingness, extremely harsh conditions. Most planets are not alive. They never come to life. But here we have this incredible miracle of a planet that not only came to life, but has remained alive, has kept itself alive for more than 4 billion years. And we get to be a part of that.
You almost bring me to tears with those thoughts. This is why I wanted to talk to you. I just love these concepts that you describe so beautifully and in such real terms. It's the way I look at the planet too, that we've been here for a nanosecond as a species, right? So much of it existed and went through all of this turmoil and growth before we even arrived. Modern man, a couple of 100,000 years ago, a little dot in the landscape of time in terms of the history of this earth. It's fascinating and drives me every day to think, how can we all love this place more so that we want to protect it more? Does it make you think about the status of the planet and Earth right now? Does it change your perception, what you've learnt about Earth and the time that we're living in?
Yeah, absolutely. I think there's a really important psychological distinction between thinking of ourselves only as inhabitants of the planet, solely as creatures that are just kind of running around, hanging on to the planet, versus being actual extensions of the planet. And that was sort of one of the biggest revelations for me in writing this book, is that I don't see life anymore just as a sort of surface, superficial phenomenon that's just existing up here. I see it as a literal outgrowth, a literal extension, a literal expression of the planet itself. So there really is no distinction between us and all life and the planet. It really is continuous. It's physically, materially continuous. And I really think that is a scientific fact. It's not just a nice notion, or something mystical. I think it is really a physical, material truth. And I make an analogy sometimes, if you think about a vast beach and all these sand castles and sculptures that kind of emerge out of the sand of the beach. Well, those structures are still continuous with the beach as a whole, right? They're still made of the same grains of sand that the whole beach is composed of. I think it's the same with us and Earth. We are literally made of Earth, of its materials. We return to Earth when we die. All life comes out of Earth. all life is necessarily made of Earth. So there really is no meaningful distinction between us and the planet. And I see all life on Earth now as quite literally, materially continuous. And that really has changed things for me. And I think we're continually refining sort of the nuances and the details and learning how this system works and what it means for a planet to be alive. Because, life is one of those concepts like consciousness or language or intelligence that we have not fully worked out yet. We don't have that precise, beautiful definition or a single equation, that can explain it all as a physical phenomenon.
Right.
So there's still very much a lot of open questions there as well.
After the break, Ferris travels the world as he searches for answers. What does it mean for a planet to be alive? He digs pretty deep. So deep, it takes him a mile underground. Hey wildlings, I hope you're enjoying my chat with Ferris Jabr. I'm excited to share with you that we'll have the extended version of this interview available for you to listen to on Patreon coming your way soon, so keep an eye out for that. Just a reminder, for a few bucks a month, you can find lots of new wild bonus content on Patreon. There's a link in the show notes. Now let's get back to my conversation with Ferris. If life on Earth started from the raw materials of the newly formed planet, then there was only one obvious place for Ferris Jabr to really go back in time to understand that.
So in South Dakota, there's a former gold mine called the Homestake Gold Mine, and it's no longer a gold mine. It's been converted into a subterranean scientific laboratory. And most of the researchers that go there are physicists, and they're performing these complex experiments that have to be shielded from cosmic radiation. So they use all this rock to do that. But I went with biologists that go about close to a mile beneath the surface of the planet in this mine, and they're hunting for these really bizarre microbes that live way down there in the Earth's rocky crust. And these microbes are very different from the microbes we find on the surface of the planet because they don't have the same access to sunlight and to oxygen, the way that surface microbes do. So they've evolved different ways of getting energy, and they might resemble some of the earliest microbes that evolved on Earth many billions of years ago.
What did it feel like going down deep underground and looking for this unseen life that's been kind of sculpting the Earth, right, for so many billions of years? What did that feel like?
Yeah, it was thrilling. So unlike the research tower in the Amazon, in this case, there is an elevator. So you can ride an elevator down. So it's a little bit easier, a little bit faster.
When you go in a mile down, that is kind of useful, yeah. Yeah.
And then you get down there, and the terrain is very varied, actually. So some pockets of it are extremely hot and stifling. You can only be in these spaces for a few minutes at a time, and you have to kind of retreat and take a breather because they're just so much closer to Earth's, internal geothermal energy. They get really hot and really stuffy really fast. And they smell of sulfur, of rotten eggs, because there's so many of these microbes, releasing these gases down there. And then other areas are much cooler, better ventilated. There's kind of wind coming down through the surface all the time. And you travel through these underground tunnels on these little rail cars, that remind me of an old theme park ride because they're kind of like chunking along. It's extremely dark. The only light is your headlamp, so you can only really see what your headlamp illuminates. And so it has this kind of surreal feel to it. It feels like something at a theme park because it has been created by us. Like it wouldn't exist if we hadn't gone down there and made it that way. I was worried that I would feel really trapped and claustrophobic.
No doubt.
But because your vision is so limited, I feel like you can't really see that you have like multiple Empire State Buildings worth of rock above you. All you can really see is that you're in a tunnel, so it just feels like you're in a tunnel.
So it seems like an ordeal to get down there. What did you find and what did it tell you while you were down there?
Yeah, we did find the microbes. There are sort of these spigots coming out of the wall, the rock that the scientists have made, and because what they want to do is they want to tap into the water that is coursing through all the pores and fractures in Earth's rocky crust. So whenever the miners accidentally hit one of these veins of water, the scientists cap it with a spigot or a faucet so they can come back and sample the water. So around these kind of hotspots, the microbes are constantly draining out through the trickles of water. And in one area, they form these pearly white milky pools because these particular microbes, they take sulfur into their cells, so they become kind of ghostly white.
And are they they're not eating the rocks, but they are, breaking it down? Or how does that affect the next building block in life? Why do you care about these microbes to the point where you take an elevator a mile underground to see them?
Yeah, some of them are eating or breathing rock and metal. Instead of doing photosynthesis or breathing oxygen the way that we do and a lot of microbes do, they've evolved other ways of getting energy that entails breaking down rock, or essentially breathing rock, moving electrons around, between different rocks and metals on their own cells. And in doing so, they are changing the mineral composition of Earth's crust. They are turning minerals and rocks and molecules from one chemical state to another. So scientists have found bacteria and microbes, deep underground that are literally creating soil. They're turning rock into soil. Sometimes they will start little deposits of precious metals like gold and silver. So sometimes the precious metal that we mine has actually been concentrated by microbial activity. And sometimes they're actually filtering and purifying underground water. So they're changing the geochemistry of the Earth's crust all the time.
The very basis of your entire book, all of this, the building block of life, but also the building block of what you wrote about in your book, right? All of this, how these microbes, these living organisms are actually changing the Earth itself. Let's come back up to the surface of the Earth now, but we're going to stick with rocks, one of those major building blocks, that you talked about: rock, water, air. I know you also went to Hawaii and experienced some sort of modern-day geology in some ways, What did you see when you went to a beach there in Hawaii?
Yeah, an extremely modern form of geology is happening there because the Hawaiian Islands act as a kind of comb in the middle of the Pacific. They kind of strain out a lot of the debris and trash that gets thrown into the ocean. So a lot of plastic pollution collects on certain shores on Hawaiian Islands. And on this one beach called Kamilo, it really happened to an extreme degree, to the point that there were piles of trash 8 to 10 feet high on this beach at one point.
Just washed up from the Atlantic. Pacific.
Yeah, just strained out of the ocean, because you have these gyres, these massive swirling currents of water, and the islands are kind of in the middle of them, and so everything that's floating around out there gets strained through the islands and gets caught in the islands as though they were, the teeth of a comb. And so there have been these massive cleanup efforts to remove all of that garbage, because this process just keeps happening. If you don't do anything about it, the trash just keeps building up. So volunteers have dramatically reduced the amount of trash out there, but the sand is still saturated with tiny particles of plastic. And when people go out there and make campfires, that sometimes melts the plastic in the sand and it fuses it to sand and shell and rock, and it forms a new geological material called plastiglomerate that scientists only discovered in the 2000s, and that's what they called it. So you can go out there to these beaches and you'll see rocks that look just like ordinary rocks, but then you pick them up and they're way too light for their size. They feel totally off. And that's because they're partly made of plastic. They're this new fused geological material. So some scientists have argued that there should be a new type of rock, not just the usual classifications that we're used to, like metamorphic and seismic and all that, but it should be called anthropic rock, because it's partly made of human engineered materials.
It's rather depressing, actually. That's our contribution to the planet.
Yeah, exactly. And this material is so durable that scientists think it will be there, even potentially millions of years into the future. There will be this signature of plastic in the rock record and the fossil record.
And this creature called Homo sapiens that once existed, maybe. Yeah. Wow. I mean, yeah, the implications of that and yeah, our historic record, what a way to leave our footprint, hey. I love how you have compared that, that we're doing this, we're creating this new form of modern rock that will be around for perhaps hundreds of millions of years, and you've compared it to photosynthetic organisms and trees. Can you describe that a little bit?
Absolutely, yeah. Photosynthetic life has had a truly profound influence on the planet, arguably the most profound, because one thing about, one of the biggest changes our planet went through is going from basically having no oxygen in the atmosphere whatsoever to being a very oxygen-rich planet. So, billions of years ago, there was basically no O2, no free-floating oxygen in our atmosphere. Today, it's 21% oxygen in the atmosphere. That's a massive difference. And that started with the evolution of photosynthesis, when microbes and then later land plants learned how to take sunlight and break apart water and take carbon dioxide and make food for themselves and then release oxygen in the process. They started to massively, profoundly transform the planet's chemistry. And so they oxygenated the seas and the atmosphere, and then that really changed everything. Because when you have an oxygen-rich environment, all kinds of chemistry is suddenly possible that was not possible before. Photosynthetic life became a hugely important part of the carbon cycle after it evolved.
Yeah, I want to talk to you a bit about these new kinds of chemistries that were suddenly possible. Something I found surprising in your book is that fire didn't exist on the planet until life created the right conditions. I think most people think that fire has always been around, but what changed that allowed fire to exist?
Yeah, that's exactly right. And it really is mind-boggling. It's one of those things that we take for granted or assume are the default state of the planet, but actually weren't around for most of Earth's history. So for fire, you need three ingredients. You need a lot of oxygen in the atmosphere. You need something dry and combustible that can burn, and then you need a spark to set it all going. So ancient Earth had plenty of sparks in the form of, volcanic activity or falling meteorites, things like that. But there wasn't any oxygen in the atmosphere, and there certainly wasn't anything dry and combustible around. So wildfire, as we know, it simply was not possible. The advent of photosynthesis, the oxygenation of the planet, and then the advent of land plants really changed everything. So once you had that oxygen-rich atmosphere and you had a lot of land plants around, then you had all three conditions in place, and that's when fire could really start, maybe some 425 million years ago or so. That's when we kind of have the oldest fossil evidence of fire in the form of ash,
back in that window of cellulose, right? Which makes perfect sense.
Yeah, exactly. Yeah, when plants are really thriving on land for the first time and really changing so much. Fire starts happening a lot more frequently, and then plants and fire start to co-evolve these really profound rhythms with each other. Basically, all terrestrial ecosystems, because they are dominated by plants, have co-evolved their own rhythms with fire, where fire is a really important part of how that ecosystem works.
And then so back to the rocks, that the plastic in the rocks, or the plastic rocks, our little human footprint that we're leaving in Hawaii. What does that teach you about the living planet, that those exist now?
Well, to me, it shows the confluence of the biological, the geological, and then the technological, right? So all of these truly novel techniques and engineering methods and substances that we have introduced to the Earth system far more rapidly than has ever happened before in Earth's history. Because, for example, the oxygenation of Earth, that happened over billions of years. There was, something like a 2 billion year process between the origins of photosynthesis and then the eventual advent of land plants and forests covering the planet. Well, plastic, in contrast, that's something that's happening over decades. Like we go back before 1950, there was no significant amount of plastic in the environment. And today, it's everywhere that we look. We find it in the deep ocean. We find it in clouds. We find it in our bodies, in our lungs and blood. It's just absolutely everywhere. That's a very, very rapid transformation. That's never really happened before in Earth history. That's what makes our species so unique and unprecedented is, the speed and the scale at which we do things. It's not like life has never changed things before. It's not like there's ever been a species that's, not introduced something new to the Earth system, but nobody's ever done it this quickly.
After the break, we'll hear how giant animals transform the Earth on a daily basis, and how you better watch out for tsunamis. As an ecologist, I've worked and studied for decades to understand how different animal species interact with one another, kind of how the whole is greater than the sum of the parts. But in his book, Becoming Earth, How Our Planet Came to Life, Ferris Jabr talks about a new way of thinking about this interconnectedness. It's called zoogeochemistry.
This is a relatively new concept in ecology that puts animals back at the center of geological and geochemical cycles. The old way of thinking is that, the way that carbon and nitrogen and phosphorus and essential nutrients and elements move throughout the planet's layers is mostly propelled by geology and meteorology. And the new way of thinking is that actually animals themselves are really important engines at the heart of these cycles, especially really big animals like elephants and whales that simply through their sheer heft just move things around so much just by existing and moving through the world. So it's all about the connections between biology and geology within these incredible loops, not just one or the other.
Talk to me about the whales, though. You just mentioned whales and elephants. Have you got an example of how a whale and its heft, as you described it, impacts its environment?
Yeah, absolutely. So if you think about, a giant creature like a whale moving through the water column, kind of diving to the depths and moving back up to the surface, it's moving a lot of water around simply by doing that. And that is mixing oxygen and carbon and nitrogen and phosphorus through the water column. And in fact, scientists have estimated that the collective movement of all the animals in the ocean mixes up seawater as much as the moon and tides and winds do.
Wow.
So all life in the ocean is this really massive geological force in that sense. And then when whales are at the surface, they release what scientists call tsunamis or tornadoes, so these massive fecal plumes that
Okay, tell me more about a tsunami. What on earth?
Well, if like a blue whale, right? Not only the biggest animal alive today, but the biggest animal that ever existed, even larger than any dinosaur we've ever discovered, that's going to be a really big fecal deposit. And so it's, that's an immense amount. That's an immense amount of nitrogen and phosphorus that plankton need, right? It's like fertilizing farmland, right? Like that's basically what whales are doing at the ocean surface is they're fertilizing the photosynthetic plankton that live up there. So it's a really important part of the marine ecology and food webs and ecosystems. Elephants do something similar on land, right? So they're also really important ecosystem engineers. They are constantly trampling trees and shrubs, dispersing seeds, and even their footprints have a really big ecological impact. So a single elephant footprint can fill up with about 50 to 60 gallons of water and become a temporary pond. Wow. That's a habitat for amphibians and insect larvae and all kinds of creatures that otherwise wouldn't have access to any sort of standing water. So simply by walking around, leaving their traces, their footprints, elephants are re-engineering the landscapes in which they live.
So these actions of animals that are impacting the physical world around us that we've talked about, you wrote about this on a personal level with your home garden. How did all the things that you learned writing this book help you become a better home gardener? Yeah,
gardening became a really important part of my life as I was writing the book, and it kind of all converged with what I was learning about the planet, and in particular about soil and how recent soil is as a development in Earth history, because like so much of what we've been talking about, soil as we know it is really a product of life, and it didn't exist before life got to work changing the planet. For most of Earth's history, it just had crumbled rock, like what you would find on Mars, and the sort of rich organic soils that we have today, that was created by life imbuing all of that crumbled rock with carbon and with organic compounds. So it's the microbes and the fungi and the plants and the animals all working together to make these fertile soils that allow us to farm and to garden on a more personal scale. And so I bought a house here in Portland, Oregon with my partner 5 years ago. And the only thing that was here in terms of a garden was just a lawn, a grass lawn, and it was in really bad shape. So we ripped all that out and we set about, creating a garden from scratch. But we found that our soil was in really bad shape as well because it was very nutrient poor. It was very hard and unyielding and unworkable. So I was learning a lot about soil science in an effort to try to understand what to do, because this was, a much larger landscape than I'd ever worked with before. And it really was impressed upon me how important it is to introduce a large number of healthy, diverse plants, because they really start all these important processes of remaking the soil. They permeate the soil with their roots, they break it apart, they open channels for air, water, and nutrients, and then they start attracting their symbiotic partners, the microbes and fungi with which they evolved, the microanimals in the soil, and then that brings in larger animals, and then eventually the plants cover all the soil with a protective cloak of vegetation, so they protect the soil's unique architecture and ecosystem, prevent it from being degraded and swept away and blown away. And so we started that process, and then the plants really did a lot of the work themselves.
Do you remember what those plants were? What were those the first pioneers that you put in there?
Yeah, so we focused on drought-tolerant natives that are suitable for the Pacific Northwest.
Right.
It's all kinds of flowering perennials, so plants that come back year after year. They make beautiful flowers that, they're pretty, but they're also important for pollinators. They often stick around and cover vegetation really well. So, some of the plants, and I use a mix of natives and non-natives. I use a lot of flowering thyme as a ground cover because it's really drought tolerant and the pollinators really like it. Recently, I've been working with something called Oregon Sunshine. It's a sort of small daisy-like flower that's native here. And purple flowering aster is also a native that is really beloved by pollinators. And we've introduced hundreds upon hundreds of species and cultivars at this point, everything from succulents to annuals and wildflowers to flowering perennials. And then we have our beds for edible crops and all kinds of things. And the soil has become richer and darker and more workable over time.
Oh, how pleasing. How does it all look now when you look out of your window and it used to be what used to be a lawn? What does it look like now?
It's so much thicker, lusher, denser, more vibrant, more diverse. And when we first moved in, we didn't see any wildlife at all. And now we have this vast array of insects and birds visiting us all the time.
Beautiful.
And I've gotten really obsessed with the native bees because there are about 20,000 native bee species worldwide, and I think around 5,000 in North America. And, so much more than just the honeybees and the black and yellow bumblebees that a lot of us are used to. And I've started documenting them. I think I've seen at least 20 distinct bee species in my own backyard in Portland and photographed them all.
Superb. Yeah. Sounds like it's become your mini Gaia back there.
Yeah.
We talked about Lovelock and Gaia. What has changed since Gaia? Why do you think things have changed since Gaia over this last very recent history in the last few decades that make us look at the planet in a different way?
Yeah, a lot has happened since Lovelock published his first book on Gaia in 1979. A lot of amazing science has happened. A lot of new insights have come to light. And we definitely have a deeper, richer understanding and appreciation for the Earth system and how it works. Still much left to be explored and understood. But I think that is a big part of why there's a lot more acceptance of this idea of thinking of the planet as a single living, self-regulating system. Whereas before, several decades ago, when Lovelock was first talking about this, it was much more controversial because we simply didn't know enough about these incredible interconnections between geology and biology.
And I guess a major one being climate change that came up after. Really, people knew about it, scientists knew about it, but it certainly wasn't in the everyday conversations as it is today, right? That seems to have triggered a lot, doesn't it? You combine that with recent science, the awareness of climate change, the awareness of the biodiversity crisis. Hopefully we're on the right path, right? All of this it makes me want to, you don't have to answer this, but it's all big stuff, all sort of heady stuff, the history of our species and the planet we live on. And are you a religious man?
I have always had sort of an innate reverence, awe for nature, for the universe itself, for its complexity, its diversity, its beauty. I find a lot of joy and inspiration and wonder in learning and understanding, how this big, beautiful, wonderful universe works. That's really what drives me, is my intense, innate curiosity about all of this. And I find that incredibly fulfilling, so that's really what propels me forward. And writing this book has just dramatically heightened that appreciation and awe and reverence that I have for nature, for the natural world and for how all of this works. And to be a part of that, to be a sentient individual that can be aware of all of this, to experience all of this, to attempt to understand it, is more than enough for me. I feel so privileged for that small miracle.
You're grateful for that giant brain that can process all of this, and that curiosity is enough. And what a great answer. If a tree in Brazil really can change the weather in the Pacific Northwest and in Canada, what else do you think that we're underestimating that we really should be paying attention to?
Well, I think we've seen throughout the history of science that we are a very hubristic species. Many times we have thought that we understood something well enough to intervene or to make a change, and it turns out that we didn't. There's so many examples. Like, one of the most famous is we thought we could bring over cane toads to Australia to take care of the beetles that were, a pest problem in the sugarcane. And that turned into this big ecological ongoing disaster. And so I think we have to be humble. We're in an unfortunate situation right now because we need to intervene and make changes as quickly as possible to avert the worst outcomes of climate change. But we at the same time need to have some humility and not think that we can just pull all these levers on these complex systems that we don't fully understand yet. Mm-hmm. Fortunately, we do know enough to know about the changes that we can make safely. We know that we can transition to renewable energy away from fossil fuels, and we can do that safely. Because that is really more about stepping back, backing away, not continuing to introduce all of these warpings, these massive warpings of the Earth system.
Mm-hmm, mm-hmm. You write that we need to stop thinking that we control the system, but that we can't also pretend that we don't have an impact, right? That we don't control the system. There's much bigger things in control, but that we still do have an impact. That sounds like a really tricky balance. How do we find it?
Yeah, it is. It's difficult to get your head around, but it is really important to understand, is that we as a species have an outsized influence on this planet. We have changed it at much bigger scales and much more quickly than any other life form before us. At the same time, we have to accept and recognize our own limitations, that we're not smart enough, we don't have enough knowledge to control the entire system. So it really is a lot safer and wiser and better to interfere, as little as possible, to stop doing things like emitting all these greenhouse gas emissions that really warp things and imbalance things, and try to live as cleanly and seamlessly as part of the Earth's systems that already exist and that have co-evolved over billions of years. And that is exactly what technologies like renewable energy allow us to do. These energy sources already exist, solar and wind and water and all that. By taking advantage of them, we can sustain and support civilization without shifting and imbalancing, the carbon cycle and all these long-term geobiochemical cycles that are so important to keeping Earth habitable and keeping it alive.
Mm-hmm, mm-hmm. I love what you do in your book, and in this conversation you tie the biodiversity crisis with climate change. It's something I'm constantly trying to do as a conservationist and an ecologist, is trying to make people see these things as very interconnected, the biggest possible picture, biggest possible scale. How the biodiversity crisis, us killing off species around the world, whether it's a chunk of the Amazon rainforest or wild animals like elephants, bears and wolves, how that impacts everything on the planet. And you tie those things so beautifully together, and I'm excited because that's the case, because I love trying to tie those things together, and sometimes I struggle to, Sometimes I try to describe to people that I think the biodiversity crisis is over the climate crisis, right? If we solve the biodiversity crisis, it would solve so many of the elements of the climate crisis that we're facing, right? The planet knows what it's doing, is what you're telling us through this book. And I love that. Thank you.
Yeah, it's absolutely all interconnected, because the two biggest ways that we change the planet are through our energy systems and our food systems. So how we power civilization, how we feed ourselves. And both of those have so much to do with how we change the planet's land surfaces, right? We're constantly converting habitat and wilderness into farmland to raise cattle or to grow crops. And we are constantly plundering the Earth's resources and shifting things around, including with fossil fuels. So if we pulled back from that a lot, if we preserved more habitat for our wild neighbors, if we restored more of those ecosystems, that would absolutely take care of a lot of the problem. That would absolutely be connected, So, it really
so
is.
Rewilding comes up, right? Just the importance of rewilding, going back in time ecologically, and a softer footprint. That combination could be so potent, right? Mm-hmm. Do you think the Earth is still resilient enough to bounce back if we let it?
Absolutely. I mean, one thing is for sure is that I really think on dramatically long timescales, geological timescales, the planet is going to be fine regardless of what we do. We're just, we're extremely important in the here and now and on timescales that matter to us. But in the grand scheme, we're really much more insignificant. And I think the planet will be able to recover from just about anything we do to it. But the real question is, can we act fast enough to preserve a version of Earth that still has space for us and for all of the other creatures that are alive with us right now? Because that's really what happens at crisis points, is that so many of the species fade away and then a new Earth has to emerge from the ashes, right? So Earth is like this phoenix that has recreated itself many times over. And so if we preserve the Earth that we've been a part of, then we can keep going. If not, Earth's going to keep going without us.
If someone's listening to this feeling overwhelmed, what's one piece of insight that you might have to help them feel less overwhelmed?
Yeah, I mean, it's understandably extremely overwhelming because we're talking about the entire world. It's a massive, massive scale problem, and it's easy to feel that no one individual can make a difference. But what I learned in part through my garden is that we can all make a difference on an individual local scale in a way that is meaningful. And that can happen in a million different ways. It could be your own miniature rewilding project in your backyard, or even on your balcony or porch with just container plants. It could be you getting more politically involved, actually like voting for the first time if you haven't before, actually calling up your representatives. It could be reading books like the books that we've been talking about. There's so many different ways that you can become engaged and become a small part of the change, because at the end of the day, all systems, all nations, all peoples are made up of much smaller individual parts, and you are one of those parts. So it's your choice, whether to be part of that larger systemic change or not.
Ferris Jabr is an environmental writer. His book, Becoming Earth: How Our Planet Came to Life, explores the incredible hidden connections between life and geology. Ferris, thank you for joining us. I've really enjoyed this.
My pleasure. Thank you so much for having me.
Thanks for listening to The Wild. If you like what you hear, share it. Tell a friend about the podcast or leave us a rating and review. It helps. And don't miss an episode. Subscribe. It's free and easy. And as always, there are some great photographs and clips from our travels on Instagram at Chris Morgan Wildlife. The Wild is a production of KUOW in Seattle and Chris Morgan Wildlife, with support from Wildlife Media. Matt Martin produced this episode. Jim Gates is our editor. Our theme music is by Michael Parker. Additional music from MusicBed and Blue Dot Sessions. The Wild is hosted, produced and written by me, Chris Morgan. A very special thank you for their kind financial support to Jill and Scott Walker, Rose Letwin, Ellen Ferguson, the Isdell family, Anna Kimball, Barbara Stallman, John Taylor, Paul Lister, Bob Yellowlease, and John and Julie Hanson. Thanks for listening. Take care of yourselves and nature, so that nature can take care of you, like she does every day.